Hi, this is Pulley Physics, Applications of Newton's Second Law. We're looking at inclined planes today as the introduction. Here we're going to be able to really start looking at changing our perspective when we solve problems, because this perspective is sort of a downhill. It's not really an X direction or Y direction motion. This is a slanting kind of a motion. All right, so here we have a block, call it mass, call it M, and it's on an inclined plane. You can give that any angle you want there. So a mass on an incline. There's our theta. So what do we do with this? My problem solving text, think back from a few lessons ago, we're going to be drawing a force diagram, labeling the force vector arrows with all the known forces, unknown forces, and angles. So we're going to get that angle included there, provide values if we know them, and identify the target. So I haven't quite identified that yet. It's going to be acceleration. Number 2, determine the most appropriate orientation for the X and Y axes and redraw your force diagram. What we're trying to do here is distill this scenario into something more pure. There's going to be a lot of ugliness to it, and we want to clean it out step by step. It's kind of like a water purification program or system that you're just trying to take a kind of gross looking water. First we're going to filter out the solid stuff, then we're going to try to clean out all the metals and just bring it to a more pure and pure state. Maybe run it through a reverse osmosis filter after that. So or membrane. There we go. That's kind of what we're doing here. We're taking this step by step and making it more pure. So we're going to redraw these force diagrams a couple of different times until it's into a very useful, refined state. But thankfully, we're just starting with a simple scenario here, just a mass on an incline, and we're not even going to be looking at friction just yet. So a couple things here. The force of friction is just about 0, and what we're looking for is the acceleration of the block. Now, if you let a block slide down a frictionless plane, its motion will be in this direction, so therefore it's going to accelerate down the slope. All right, so even with just an angle, even if you don't know the mass, we're going to find that we can figure out an acceleration rate. Just ask Galileo about dropping things from towers of Pisa. So I guess there's only one tower. All right, so here's our scenario. We're going to first draw a force diagram. And it's okay to give a reference. Got a little reference angle here. I'll call that theta. In the end, I'm going to apply 30 degrees, but for now, I'm going to leave it as theta. There's a gravitational force, a weight. And I'm just going to go ahead and call that mg. We don't know what m is, but we know how to substitute mg in for the weight. And there's also a solid surface, this normal force coming up from the surface there. So there's the normal force. All right, with friction, if there were friction, we would add some friction. The block would tend to slide down the slope, and friction would be working in the opposite direction of that slide. But we're saying this frictional force is essentially 0. So this is it. Just normal force and weight is what we're looking at here. That's our first force diagram. I've identified the target variable already. So let's look back at that problem solving text. Step 1 is done. Step 2, what is the most appropriate orientation for the X and Y axes? Well, think to yourself, what direction is the acceleration in? If this system or this block were falling straight down, then the Y direction would be probably the most appropriate. The vertical direction would be the Y. And we'd be looking for an acceleration in the Y direction. If this were like a side-to-side kind of a slide, then the X direction suffices. Horizontal is good for X. Y is good for the vertical is good for the Y direction. But in this scenario, the acceleration is at an angle. We want our equations, when we get back down to Newton's second law, F equals ma, we want those accelerations to be in either the X or the Y direction, not both, like we'd see here. So if I filled in just indicated an acceleration direction, you see this is in the downward and left direction. Of course, you can't see that because my problem solving text is up. So that acceleration is in the downward and left direction. So I want you to do something highly technical here. I'd like you to tilt your head just a little bit like that to the left. Okay, so if you tilt to the left, you're going to see that the normal force is now in the up direction, and the weight is kind of down and to the left. However, what we're doing is transforming this into a situation or scenario where our acceleration will be in the x direction, to the left. So we want our acceleration to be down the slope, parallel to the slope in the downward slope direction. And when we oriented our head like this, then all of a sudden the normal force is up. That's our positive y. And the weight is now at an angle. Okay. Now, big question. What is theta? Where's theta? Is theta here, or is theta here? Okay, which one is it? So there's a couple ways to look at this. If you take just take a flat surface here, and I'll use a yellow pen. All right, here's my phone and a yellow pen. There we go. So right now, if you've got a flat surface, weight is straight down. Now, if you incline that surface, you'll notice that the weight direction stays the same, even though there's an incline. Okay. And now what we're going to be doing is rotating our view so that up is coming out of the surface. Well, what does our view do then to the direction of the pen, the direction of weight? So however much we incline it, you'll notice when we bring it back down, the pen has rotated that far, that angle of the incline. All right, so if this is our angle of incline is like about 30 degrees, you know what, I'll make this the other way so it looks like your slope there. Okay, so this is our angle of our incline. It's about 30 degrees. If we look at that and rotate it back down, then you'll notice that the gravitational force vector also rotates from 30 degrees, but from the vertical direction. So if we bring that, again, we bring that incline down and rotate it by 30 degrees, the force of gravity, that vector rotates by 30 degrees also. So the big point in here is just conceptually, when you're drawing these or redrawing this orientation, gravity is going to be angled from the vertical. It is a vertical force, and the gravity is originally, if this were on a flat plane, gravity is perpendicular to the surface, so gravity is from that vertical reference point. All right, so all being said, I think we have accomplished our step number 2. Redraw the force diagram if the axis orientation differs from the force diagram step 1. So we redrew it. We're refining this process, refining this force diagram a little bit. Number 3, we've got an angled force. The weight is angled. Weird, right? It's not in the y direction this time. It has an angle. So we're going to resolve this into x and y components and draw a new force diagram. So here we go. We're going to keep that normal force. It's in our new established y direction. And the weight is broken up into 2 components. Now normally if you've been doing projectiles for a while, or you sat for my statics lesson just one lesson ago, you might remember that the horizontal component was the cosine. Well, here we've got the weight is referenced from the vertical side. So if we consider this as a right triangle where the left-hand force is the same as the bottom part of this triangle, then we can see that the vertical side is adjacent to the angle reference. So this vertical component is the cosine component. And when we draw a downward arrow and a left-hand arrow to replace that weight, then this FG cosine theta will be downward. That's the side that's adjacent to the angle. And that makes the left-hand component FG sine theta. All right, there it is. That's our refined, purified force diagram, because now all the forces are in the x and in the y direction. So if we're solving for the acceleration, what I would do is start with that direction first. Let's see if we can figure things out with just the x direction. So we're going to sum the forces in the x direction to begin with, equals MAX. All right, so in the x direction, we have only Fg sine theta, weight times the sine of the angle, that incline angle. And that equals mass, unknown mass, times acceleration. Now the acceleration here is going to be only in the parallel to the surface. That's why we picked this as our orientation. So we would only have one acceleration. The acceleration in the y direction is going to be 0. There's a component from the weight pulling down into the slope, and there's a component from that weight pulling parallel to the slope. So that end of the slope, that y component of gravity, is going to cancel out the normal force. It's not going to accelerate this way. It's only going to accelerate parallel to that slope. So the a in the x direction is the a value, the acceleration we're looking for. It's this one. That's our x direction. Okay? It's our x. Don't want to get that confused with displacement, so I'm going to take that away. All right, so at this point, wow, there's a lot of stuff going on here. I got Fg sine theta equals ma. I'm supposed to be coming up with a value for this. So let's go back to that text, problem-solving text. Number 4, we're applying Newton's second law in both x and y directions. Oh, substitute expressions for forces where appropriate. So this is where it's really important that instead of having Fg, instead of having the weight there, we're going to substitute mg for that weight. Mg sine theta equals ma. Now look what happens. Do you notice that something's going to cancel here? If we divide m on both sides, keep the equality, we end up with g sine theta equals the acceleration down the ramp. That's it. So now all we need is to substitute acceleration due to gravity is 9.8 meters per second squared on the surface of the Earth, and whatever angle is, and I picked a nice convenient angle, sine of 30 is 1/2. So our acceleration is going to be 4.9, half of 9.8 meters per second squared down the ramp. Booyah, there it is. And that's solving these inclined planes. Okay, it's just getting there for starters. Now, there's one little piece I don't want to just gloss over, because when we start studying friction, normal force is going to be very important. And obviously on most planes, inclined planes like this, friction is not negligible. So I'm going to take this moment to talk about the y direction, and I'm not going to do anything fancy. I'm just going to sum the forces in the y direction. That's what Newton's second law tells us to do. And what do we find? We've got, in the y direction, we've got normal force up and Fg cosine theta down. So normal force minus Fg cosine theta equals mass times, okay, what's the acceleration in the y direction? Remember, our y direction is this way. The block is not jumping up perpendicular to the surface, and it's not sinking into it. The acceleration in the y direction is 0. Okay, that's 0, to make a note of that there. And also in this step, we're going to substitute mg for the force due to gravity, or the weight. So I'm going to have an mg cosine theta equals 0. All right, so that you can see that this wasn't going to help us to determine the x direction acceleration down the ramp, but what does it reveal? This reveals that the normal force on an incline is equal to the weight times a cosine of the incline angle. Bonus material here. What this is telling us is the pressure between the pressure force, okay, between the mass and that incline is equal to the weight when the incline is 0. When theta equals 0, cosine of 0 is 1. Okay? So when the incline angle is 0, the normal force is equal to 1 times mg, which is the weight. That's what we expect. If there's a block sitting on the floor, or a football sitting in the grass, we'd have weight down and an equal amount of normal force up. Those two would be canceling each other out as as balancing forces. Okay, let's get rid of that for now. But what happens as theta increases? So as theta increases to 90, if we've got a straight up wall, okay, if I try to put an object on a wall and let go of it, that wall doesn't support it at all. It would have to be inclined in order to support it. That phone wants to slide down this way, down my arm, because there's an incline. So my arm is partially supporting the object when it's at a large incline, but it's not supporting it at all on the vertical. Okay, it is completely supporting it when it is at 0. So right now the weight is equal to normal force, and as I increase that angle, the normal force will be decreasing. It goes from a maximum of 1 to a minimum. Cosine of 90 degrees is 0. So there's a percentage type of multiplier here with this cosine theta. It's going to be a fraction of mg, or partial. So we're going to be coming back to that. And the thing that you can take away from this is, in general, when you've just got a mass sliding on a plane, the amount of acceleration down the slope is what? This acceleration is g sine theta. So you can take that with you, g sine theta. Okay, so that's the other aspect. Here we get the normal forces related to the cosine of the theta. The acceleration down the ramp is related to g sine theta. So if you ever needed the amount of force down the ramp, of course, just plug an m in front of that and you get an mg sine theta. Okay, that'll be the force in that direction. So I hope this has been informative and turns out to be helpful. Next thing you might be doing is combining pulley systems with inclined planes. And if that's the case, make sure your component of force pulling the system down the ramp is that mass times g sine theta instead of just an mg. All right, it might be helpful just for me to draw out what I'm talking about. It's only take a second. So if there is a pulley and you see a system like this, see there's an M2 and an M1. Okay, of course M1 is going to be pulled down by M2 is going to be pulled down by force M2 times G, but this side is going to be pulled down by force M1 times G sine theta, where theta is the angle of the incline. Okay, so there you might get a system. If you're looking at the system model, got a mass 1 and a mass 2 being pulled to the right by M2G and to the left by M1G sine theta. So that's what you can take away from this, and I hope it's helpful.